Hey everyone. Before we get started today, I have a huge announcement to make. This Saturday, October 25th, at 2:30 p.m. Eastern Standard Time, many of the authors from the show, some new faces, and I are teaming up with the Fields Institute for Writing Math. It's a live session all about how math meets storytelling. If you've ever wondered how to market yourself to a broader audience, talk about complicated math to anyone, or how to capture an audience without losing your readers, this event is for you. It's free to join, both in person and online, and you'll find the registration link in the show notes. So come hang out with us and learn how to make math sound as beautiful as it truly is. And if you're still wondering if this is going to be for me, because I'm not a mathematician, it is. You already listen to the show regularly. This time, you get to ask the guests questions about their work live. Also, you can email me questions that you may have as well. So go sign up and hang out with us. We can't wait to see you there. Every so often, humanity does something that feels less like invention and more like instinct. We build rockets, hurl ourselves into the void, and call it exploration. But maybe, as Dr. Caleb Scharf, astrobiologist and author who works at NASA, suggests, it's really biology. And we're doing what we've always done, spreading, adapting, and reaching out for what's next. In his book, The Giant Leap, Scharf argues that when we leave the Earth, it's not just humans stepping off the planet, but it's life itself continuing its 4 billion year experiment. So, welcome to another episode of Breaking Math. I'm your host, Autumn Fanav. And we're asking, what if the cosmos isn't something we explore, but something that's exploring itself through us? Caleb, your book opens with a bold premise that humanity's move into space isn't just an adventure, but it's a new phase of evolution. You describe it as almost as a cosmological event. So let's start here. What inspired the term dispersal? And you frame humanity's push into space as not just an exploration, but as a continuation of life's evolutionary story.
It sounds very grand when you say it like that. Yeah, so, the idea behind dispersal is that when we try to make projections about the future, it's obviously extremely challenging. So what are the things that are a given? If, for example, our current efforts at space exploration continue to grow and accelerate, which is what's happening right now, things are accelerating all the time. We're heading towards a point where there'll be a rocket launch every single day of every year into either orbit around the Earth or further afield. So, what's the extrapolation from that? And dispersal is the idea that a species like us, along with organisms that will carry along with us on our journey, will move into a landscape that it hasn't experienced before. So life on a planet can feel spacious, sometimes kind of sparse. If you go to the deserts or Antarctica on Earth, it can feel like life is very sparse and spread thinly. But that's nothing compared to the landscape of our solar system. Solar system is a vast place in space and to some extent in time because of the finite speed of light and how signals take time to cross that space and so on. So dispersal is really a statement about sort of a condition that will face a species that becomes truly a true space explorer and spreads itself, which is a process of dilution and diversification, to put it in simple terms. So the idea of dispersal is there's so much space, there are so many resources in our solar system that a species that continues to advance its exploration, continues to advance its movement away from its point of origin on a planet, is going to become extraordinarily diluted and dispersed. And that dilution and dispersal may result in new things happening to that species that are almost beyond its control. So, for instance, on the Earth, we know that if a species populates new environments, over time it likely changes, it speciates. It goes from being one species to many different species. And the dispersal is about that process as well, that the future of humanity, and this is not, in the next decade, or the next century. This could be much, much further down the timeline. And the future of humanity, the future of our species, is actually a dispersed entity that turns into many new species. So the future of us out in the solar system is not going to really be us. It will be descendant species. It will be greater diversity. It will be species that are more isolated from each other because of the nature of the scale of the solar system. And so the idea came out of really trying to articulate what the options are for a spacefaring species.
So, as we're looking at different species, we also look at the fact that the universe is becoming aware of itself. What does that mean in concrete scientific terms? And why does that matter?
So this term that people do use, which is that the universe is becoming aware of itself, is really about the observation that if the universe began in the Big Bang 13.7 billion years ago, it had very little structure. Matter was dispersed in unstructured form. There were no complex molecules. There were no complex structures. It was all kind of uniform and boring, and mostly hydrogen and helium. And it took at least the first billion years before heavier elements were formed in the interior of stars. Those stars formed because of gravity. Gravity pulled together matter where it was a little uneven in the early universe. And eventually, the universe starts to build more and more complex structures. Now, that itself is a bit of a mystery. Why does the universe do that? And we can talk about things like the growth of entropy and thermodynamics, but the emergence of complexity is still a bit of a puzzle. And then the really extraordinary thing is that at some point, certainly here in this one place in the entire universe, on the Earth, we know that sufficiently complex structures formed that were able to encode in themselves information about the external world and to process that information in order to take actions that further increase their chance of surviving into the future. That's part of what we call life. And so, we perhaps live at a special time in the history of the universe, at least, from our perspective, where this emergence of awareness of structures complex enough to decode what's around them, to actually, or rather encode in themselves information from the surrounding universe, whether it's in symbolic representations or presumably in biological organisms, it's sort of part of the encoding in their DNA, and the expression of genes is related to what surrounds an organism. And so that awareness of the universe becomes a factor in the future evolution of a structure, of an organism. And so it's kind of remarkable that perhaps it's not so surprising that we're sitting here thinking about this, because we're at a point of time in the universe where this is possible, at least here. And it may have been possible much earlier in the history of the universe, but we don't know that for sure. And that plays into many, many aspects of change in the universe. Self-aware organisms that can decode the environment around them and take action on that information necessarily alters the environments themselves. And of course, life on Earth has been continually sculpting and resculpting the nature of the environment that it finds itself in. And I think it's particularly interesting to think about that in the context of our space exploration. We've now got to a point where our encoding of information about the universe, our awareness of the universe, and of course we are of the universe, so we don't sit outside of the universe, has taken us to a point where we're incorporating information from not just the Earth, not just what's immediately around us, but further and further out into the cosmos. And that is driving new change in our environment and therefore in us. So that's maybe a partial answer to your question.
Is the change really going to be more biological than technological?
I think that's an open question. It's a really interesting question. So humans and other species do this to some extent. You can look at other species and say, well, they have sort of technology. I mean, a bunch of termites that build an elaborate nest with ventilation systems and so on. That's a form of technology, one could argue. But humans do this to a much greater extent, it appears, than any other species on the Earth. We express our ideas in structures around us. We build things that modify the environment for us. And space exploration right now is kind of the premium example of that. So I think you've put your finger on something really important, that life beyond a planetary origin for biological organisms may inevitably be life plus technology. It's not like I could drop down on the surface of Mars without a spacesuit, without anything, and survive. I'd last about 30 seconds, something like
Right.
that. And so the future is more likely to be an increasingly intertwined system of technology and biology as we move away from the Earth.
So let's step back in time a little bit here because you discussed the historical inspiration of Darwin and the beagle in your book. Do you want to go into that a little bit so you can see how the evolution of what Darwin talks about and how space exploration is being discovered today and the parallels between it?
Sure. Yeah. So as I worked on this book and researched how to tell the story of space exploration, it became clearer and clearer to me that one has to look at it through the lens of natural history. Space exploration, I think, is it's a phenomenon. It's something that's emerged out of us as a species, and it's best understood. Its implications, its past, its present, and its future, its implications are best understood, as a form of natural history. And so it made sense to look for parallels in the past to the current enterprise of space exploration and the consequences of that. And it became clear to me that Darwin's experience, and particularly his voyage on the Beagle, so this was this journey on a sailing ship built by the British Empire in the 1830s, the early 1830s, when Darwin was a young man. He was in his early 20s. This was a famous voyage that literally went around the planet. It was a planetary expedition for 5 years. And there are parallels that are somewhat mundane and trivial, but interesting. And then there are parallels that are much deeper to do with this idea of evolution that, of course, in part emerge from that voyage. So the more sort of straightforward parallels are when you look at an expedition like the voyage of the Beagle, you realize that it had many, many similarities to space exploration. You had this vessel, this craft. It was an extremely carefully constructed craft. It had been customized and modified to encounter sort of unknown environments as it went around the world. It had the latest technology on it. This is something I hadn't really understood, but the ship was, before its voyage that took Darwin, it was modified to make it resilient against things like lightning. It had metal plating on it. They swapped out the iron cannons on it for bronze or brass cannons because those would influence the compasses they had on the ship less because it would change the interaction with the Earth's magnetic field. They had 22 chronometers on the ship in order to keep track of time because time was key for navigation. If you knew the time relative to some datum, you could always figure out your longitude. But they didn't want to rely on just one clock. They had 22 clocks to test and keep track of. So it was this remarkably sophisticated technological vessel that also had a very sophisticated crew. It had specialists. It had people who were handpicked to serve a certain purpose. So all of it looks like modern space exploration, but, more than 100 years earlier. But the more profound piece of this was when you look at what happened during that voyage. So that voyage enabled someone like Darwin to be exposed to a remarkable amount of information about the world, to things he'd never imagined before, to living systems he'd never encountered before, and so on. And so that sort of overview effect of the Earth played a role in his later work on the origin of species and the development of a theory of evolution, the development of a theory of natural selection and its implications for the change in organisms over time. And that work, Darwin's eventual work, which in part was catalyzed by the voyage of the Beagle, actually changed us as a species. I mean, this is the irony, I think, of his work on evolution. His theory of evolution caused evolution in us and through us in all of life on the planet. And it did that because it changed our approach to things like how we grow and breed our food stuff, how we engage with other species on the planet, whether it's plant life or animal life, and the ways we think about processes like feedback and change in the world. These were all profoundly impacted by Darwin's theory of evolution. And I argue that space exploration is doing the same. And there's a really great lesson to be learnt from Darwin and the Voyage of the Beagle, both to do with the technicalities of exploration, but also to do with what changes in the world when you move beyond the familiar, when you learn more about your own planet. And of course, space exploration has done that for us. Satellites now sense and image the planet on a daily basis, and that's fundamentally altered our relationship to the planet. But of course, we learn about other places, and it creates new possibilities for life in orbit around the Earth and further afield. So that's a rather long-winded response to your question, but
that's okay.
It's a deep connection.
It's a thorough answer, because you went into the history of this quite a bit. And I'll say history repeats itself.
Absolutely.
And you also go into Emily du Châtelet and some of the other scientists that throughout history, whether it's been Laplace, Lagrange, all the way up to Einstein and Newton, and how they changed the world and all of the universe's meanings, right? Do you have a favorite story or two that you want to highlight? Especially, it's such a long evolution.
Yeah. Yeah, so part of what I wanted to explore in the book as part of this sort of natural history of space exploration is to ask the question, so why hasn't this happened before? Why has it taken 4 billion years for a species to figure out how to intentionally remove itself from its point of origin by lifting off the surface of the planet? And some of the explanation for that is just energetics. It's that power density in biology is very different than what you need to accelerate matter or objects to the point where they can be in a sustained orbit around a planet and so on. What I realized in thinking about that was that it took human thought to make that breakthrough. It wasn't a biological trait in terms of, growing an extra pair of wings or somehow developing a propulsion system like, the way that some aquatic animals propel themselves around by squirting water. Those weren't the things that allowed us into space. What allowed us into space was human thought. And you mentioned a number of the characters in that story.
Yes.
And to me, I wanted to find new voices to tell that story. We've all heard of Newton, right? And we may have heard of Laplace and Lagrange and so on, and Leibniz and all of these people who are engaged in sort of some of the frontier pioneer work. But the truth is, it always takes more than a few key figures to make a profound change in human thought. In this case, that would lay the groundwork for space exploration, 400, 300 years later. And so some of those stories were really interesting. And I picked, in particular, 3 really extraordinary women who played a role across about 3 to 4 centuries in this story. And so you mentioned Emily du Châtelet. So she came around not too long after Newton. She was essentially a French aristocrat of a sort. She was also this remarkably bright and energetic person. She was married, but she also had a sort of lifelong affair with Voltaire. Just to give you a little snippet of, the colorfulness of her life. She was pretty good at gambling, apparently. She was, she enjoyed life, but she was also a remarkable intellect. And one of the things she did was help translate Newton's works into French, which gave access to the entire sort of network of French philosophers and natural scientists in a way that wouldn't have happened without her. And not only that, she helped push along these ideas about concepts such as energy. And energy is a really weird concept because it's not a thing per se. And we often get trapped in that, the science fiction stories, Star Trek, it's a being of pure energy. Well, that doesn't make sense. Energy is a characterization of the world that expresses something about how things can change in the world. You need energy for things to change. And du Châtelet kind of got to grips with this in a way that hadn't happened before. And so she was this catalytic phenomena. And so I wanted to tell that story because it was so interesting and her life was so extraordinary. She died tragically young because of childbirth, which obviously was pretty perilous in those times. But she injected a huge amount into the development of physics, the development of ideas around things like energy and movement, the laws of motion, all of which laid groundwork for eventually space exploration. But then there are other people like Mary Somerville, who came somewhat later than Du Châtelet, and Somerville was an extraordinary mathematician who also worked on really decoding some of these very very esoteric and hard to pass mathematical frameworks that people like Legendre and Laplace had formulated. But she was able to further develop those frameworks, and so she studied things like the principle of least action, which is a central principle that kind of tells you why if you roll down a hill, you roll in a straight line usually. You don't take some meandering path. You will take the shortest path between 2 points. And that is also an extremely important concept for when we're thinking about movement in space, in orbits, and so on. And she also helped sort of work out the mathematics that would allow us to make predictions about the orbits of planets. And she was someone who, had been married off at an early age, but then, I guess lucky for her, the husband died at an early age, leaving her with time on her hands and some money in the bank, and she was able to pursue her interests. And then you get to, in the early 20th, people like Emmy Noether, who was one of the most brilliant mathematicians of the early 20th century. Even Einstein agreed on that fact. And she took ideas like energy and momentum and the fact that those quantities tend to be conserved in the universe. So a system, you can evaluate the momentum of a system, which is the product of the mass and the velocity of objects. And what you find is that, in general, momentum is conserved or preserved through time. Things can change. If you have a pool table and the balls bouncing off each other, it looks like things are changing, but the total momentum of all those balls tends to be conserved. It tends to be the same sum total over time, which is kind of strange. But Noether took this step back into very abstract mathematics and proved that the conservation of things like energy and momentum, which are so important for understanding rocketry and space travel, are, the conservation of those quantities is a result of deep fundamental symmetries in nature. The fact that physics today is the same as physics tomorrow, as far as we know, gives
so far
rise to things like the conservation of energy. And the conservation of momentum comes from the fact that something is the same when it's placed over here as it is when it's placed over there. These sound almost too simplistic, but they're actually really important fundamental theorems that she was able to prove. So anyway, what's interesting about their stories is that they really lay out this progression in human thought, that all the pieces were falling into place for that step of application into taking us from the surface of the planet out into the universe.
So let's shift a little bit as we're going out into the universe. July 20th, 1969. We ended up on the moon. Was our first lunar landing. And it was 71 attempts before that. And many of the attempts, it was the big space race against the Soviets. And granted, they might have landed before that, but there were some crashes.
Definitely.
So, yes, the lack of readily stable low orbits around the moon can be a spaceflight headache, but it's also a direct window to a complicated and violent history that is also connected with Earth. Tell us more about that.
This is a big story. So one of the things that came out of the Apollo missions and some of the other lunar exploration, as you say, there were a lot of attempts and a lot of things didn't work and a lot of attempted robotic landings on the moon and so on. But one of the experiments that the Apollo astronauts took part in wasn't actually on the lunar surface. It was in orbit. So before some of the Apollo missions returned to the Earth, they actually left behind in orbit these small sort of sub-satellites, these kind of suitcase-sized satellites, which is kind of interesting. It's something people aren't aware of, that they didn't just perform experiments on the surface of the moon, the astronauts, they did some of this stuff in space. And what was really intriguing was that these suitcase-sized satellites that were left, and they were left to monitor certain things like radiation and to perform some sort of simple scientific experiments long after the astronauts had left. Those satellites had a hard time staying in orbit around the moon. They were orbiting fairly close into the moon. There's no atmosphere, so you can orbit not far above the surface. But the orbits seemed unstable. And to cut a long story short, what was realized from that and from later study, in fact, study that continues to this day, is that the moon is very lumpy and bumpy in its interior. And I think, in school, we all get that sort of lesson on, the interior of the Earth, where you have a cutaway and it looks like an onion with different layers. There's a core, there's a mantle, there's a crust, and it's all sort of very symmetric. The truth is, an object like the moon has enormous variations in the density of material in its interior. It's not a perfect onion. It's kind of a slightly moldy, lumpy onion inside. And those variations in density mean that its gravitational field is not perfectly symmetric. And that's what those satellites were experiencing. They were experiencing a non-uniform gravitational pull as they went around the moon, and so their orbits were not necessarily very stable. So why is the moon like this? Well, that really was the beginning of this remarkable story of decoding the origins of the moon. And what we think is the current best picture of where the moon has come from is that it's essentially come from us. But it's more than that. It's come from the results of an enormous collision some 4.5 billion years ago between an object that was sort of proto-Earth, a planet-sized object that was the Earth before this collision, and another object that may have been the size of Mars that collided with the Earth, material from those two objects apart, then remixed it. And the moon then formed as a satellite around the remaining proto-Earth. And as a consequence, the material of these two earlier objects got mixed together. And so in a very real sense, the moon is the last untouched piece of us. The Apollo mission also, or the Apollo missions and the astronauts' samples that they brought back also told us that the composition of the moon is almost identical to the composition of the Earth in terms of the rocks, the silicates, the carbonates, and so on, and all the isotopes of the elements that you find in those materials, which sort of further supports this idea that we kind of formed out of the same stuff, which is really remarkable. The moon, you look at the moon in the night sky and you think, well, yeah, it's beautiful, but it's this other thing, right? And we know it's 250,000 miles away. But it really is like looking at the last great desert on Earth, or the last great piece of the South Pole that's been unexplored. It's a wilderness. It's as much a part of us as we're a part of it. So it's a good story.
But don't people still crash into the moon until today? There was this one story that you had, it was 2019 with an Israeli mission.
Yes.
Why is that? Why haven't we gotten it right now? Because it's close.
Yeah, no, space is hard, right?
Yeah.
So, getting spacecraft down onto the surface of another world is extremely difficult, even if it's the moon, which is relatively nearby. And I mean, you already mentioned, prior to the Apollo landings, there were many attempts. Back at that time, in the 1960s into the 70s, some of the challenges were things as crazy sounding as just not knowing exactly where the moon was at any given time, which may sound very bizarre, but if you think about it, how do you measure exactly where an object 250,000 miles away is? You can use radar, you can use, telescopes and so on, but, getting the precision of knowing exactly where the moon will be when you arrive in your spacecraft, down to, hundreds of meters, is difficult. And to some extent, that's still true, although we've got much better at that. But the truth is that the sorts of speeds and precisions required of trajectories of spacecraft to get them to a place where they can land safely on the surface of an object like the moon, not crash, where everything happens in perfect sequence, is still incredibly challenging and difficult to do. And it's because it's a mixture of electronic sensing and mechanical hardware. You have rockets and thrusters, and they can experience variations in the thrust they produce. They maybe don't switch on in exactly the millisecond that you need them to switch on, and there can always be other factors. Some piece of the spacecraft may have shaken loose, and it changes the profile of the spacecraft and how it responds to the thrust applied to it, and so on. So absolutely, yeah. So we're still crashing things on the moon, and even just within the last 12 months, been efforts in this increasing effort to have commercial providers send spacecraft to the moon, cheaper and better. That also runs into these challenges, and each attempt you learn something, but the trouble is then you've got to do it all over again. You can't just it's not like a video game where you just reset. You have to rebuild, relaunch, and go through it all again.
Let's actually take a little bit of this space exploration into what happens to us, humans, animals. We've had various missions here. Essentially, everything from your heart, your eyes, you get stomach problems. We haven't even touched on microgravity. Tell us some of the effects of humans and animals going into space, just for the very basics.
Yeah, well, so almost since the beginnings of putting animals into space, humans into space, perhaps the biggest difference is an absence of gravitational acceleration when you're in an orbit or when you're floating out in the middle of nowhere in the universe. Here on Earth, we're subject to a constant gravitational acceleration. In the space station, you're orbiting, and that means you experience close to zero gravity, or so-called microgravity. I mean, in an orbit, there's always little deviations and changes. That has profound effects on our physiology, on human physiology, on the physiology of other creatures, even on the stress responses of microbes. Everything on Earth has evolved in a gravity well under constant gravitational acceleration. So put a human in space, the first things that happen are that your body's trying to arrange the liquids inside of itself. That starts to go wrong because there isn't a sort of uniform acceleration towards your feet. So liquids in your body will end up in places that they're not usually. Some of that changes and sort of gets corrected as your body adapts. But astronauts talk about having sort of swollen heads and skinny feet. And it's because your body is desperately trying to place the liquids at your blood or your lymphatic system in the right place, but it can't because there isn't gravitational acceleration. Your cardiovascular system responds and has to try to figure out what to do, how to circulate your blood efficiently. Even your breathing, the diffusion of oxygen in the membranes in your lungs is modified. Your bone density can change quite dramatically and quite quickly in zero G. And this has been one of the big challenges for astronauts who spend a long time in these conditions in the space station is you'll suffer bone mass loss or bone density loss. You get osteoporosis, essentially. And that's problematic, obviously, when you come back to Earth. You don't want to suddenly be a bag of jelly when you get out of your spacecraft. But it also causes problems for your kidneys because the calcium in your bones leaches into your blood, into your blood plasma, and then that's filtered by your kidneys. And so you can get kidney stones because your bones are essentially dissolving inside you. And your microbiome gets strongly perturbed and disturbed. And that's something that's been studied a lot in recent years, as we've learned that the human microbiome, these are all the bacteria and archaea that live in us, in our digestive systems and are part of our immune response, they get stressed. So that population changes, and that can cause stomach problems. There's questions about sleep. It's hard to sleep in microgravity. Your vision can be impaired because the shape of your eyeballs can change because there isn't gravitational acceleration on your eyes, and so on and so on and so on. I mean, it doesn't make it sound very attractive, but obviously we've also figured out ways to mitigate some of those problems.
But if we're looking at not just immediate space exploration, you said even for long term, we're thinking about exploring other worlds, other planets. We've started looking at some of these other planets since what, 1958 ish, when we put probes out to the moon and to Venus. But now, also with Mars and its sites, tell us about why we wanted to explore all of these other planets, just not just in our solar system, but also there was some exploration for Venus in like 1962 as some of the early days. Tell us a little bit about that.
Right. Well, I think it's part of what I wanted to tell in the book is this story of the sheer amount of exploration that has taken place since essentially 1957 and the launch of
Yes.
Sputnik, which kind of was a sort of proof of concept that we could put things into space and have them there for an extended period. Almost immediately after Sputnik was launched and went around the Earth, both the United States and the Soviet Union made all kinds of plans for interplanetary exploration. So the moon was an obvious target, but then so too were Mars and Venus. And, there were plans afoot by the early 1960s and spacecraft being launched in attempts to reach other worlds, whether to fly past them or even eventually to go into orbit around other planets. And that had its problems. There's a famous example where the Soviets were trying to send a probe to Venus. And again, you had to do that, you had to know where Venus would be when you arrived.
Right.
And that was challenging. The precision needed to pinpoint Venus to within even a few thousand miles is pretty serious precision using Earth-based telescopes and measurements. So they were using things like planetary radar, extremely powerful radar pulses out into the solar system to get the bounce back in order to locate the planets. And there's a famous example where the Soviets, reasons that are still a little bit unclear, sort of mislocated Venus by something of the order of 100,000 miles. And there's a nice sort of Cold War story there where the US learnt of this and basically poked fun at the Soviet Union, right? It was a good piece of PR
Yes.
in the Cold War by saying, well, apparently the Soviets have discovered another planet orbiting the sun, ha ha ha, because they don't know where Venus is. So there's some really interesting aspects to those early stories where nobody had done this before. Right? They were hashing out the fundamentals of space exploration. How do you find where a planet is going to be when you show up there? How do you power your spacecraft? How do you stabilize your spacecraft? How do you navigate in space? These were all things they had to do from scratch. So it's a really interesting history.
But when we're launching to these other planets, you talk about Lagrange points. What are they? Because I know some listeners, they may be going, what? What is that? And apparently in 1970s, they had a $1 billion budget for deep space exploration. Was that one of the calculations?
Yeah, so so Lagrange points are an interesting phenomena, and they're quite hard to get your head around, but they play an important role and have played an important role in space exploration because of what they provide for us, as well as just being a natural phenomenon. So, we're used to thinking about gravity on the Earth, right? It's pulling us in one direction. We understand that if you move further and further away from the Earth, that gravitational pull weakens. Similarly, we're used to thinking about, well, there's the moon orbiting us, and the moon is orbiting us because of the mutual gravitational pull between the Earth and the moon. And that's kind of how orbits work in some hand-wavy way. But it turns out that when you look at the mathematics of objects that are in mutual gravitational attraction, like the Earth and the Moon, or the Earth and the Sun, or the Earth and the Sun and the Moon, and all the other planets, and in constant motion in these orbits, there are these weird places, these weird points in space that they're not on the surface of a planet or the moon. They're just out there in space where things sort of balance out. Forces kind of balance out, or at least you can sit in those places and be much less disturbed by the pull of gravity of other objects. But the locations of those places is kind of unexpected, I think, if you hadn't really thought about this. So there are these locations that lie between somewhere like the Earth and the moon. there's a sort of balance point. If you took a straight line journey from here to the moon, there would be a point some distance from the Earth and towards the moon where essentially you wouldn't really feel a pull one way or the other, but you would still be moving with the motion of the moon around the Earth. And that's what's called the L1 or Lagrange point 1. It's sort of a balance point between the Earth and the moon. That's not so hard to conceptualize because you think, well, yeah, the moon is pulling, the Earth is pulling. There'll be a point of balance where they sort of equal out, they sort of balance out, and you're not going to get pulled in one direction. It's complicated by the fact that everything's in motion, that the Earth and the moon are orbiting around each other or around a common center of mass. And so that makes the calculation a little more complicated. And of course, it was Lagrange, whose name is attached to this, who really made these computations. But it doesn't just stop there. There are other points. There's a L2 point, an L3 point, and an L4 point, and an L5 point, which are these locations in space around a system like the Earth and the Moon where things kind of balance out. So, for example, on the far side of the Moon, a certain distance is the so-called L2 point for the Earth and the Moon. And that also is a kind of a point of balance. You could sort of hover a spacecraft there and it will orbit in sync with the orbit of the moon around the Earth, even though it's further away from the Earth, which is kind of strange. So you can always have the moon between you and the Earth if you sit in that point, which may not be terribly useful, but it is what happens. Then these other points, like the L4 and L5 points, actually sit in the same orbit as the moon around the Earth, but ahead of the moon and behind of the moon in orbit by about 60 degrees of arc, if you think of a big circle representing the orbit of the moon. And those places are also in sort of somewhat stable locations. In fact, places where natural material can accumulate over time. And we don't see too much of that in the Earth-Moon system, but the same kind of phenomena happens, for example, for Jupiter and the Sun. There are L4 and L5 Lagrange points in that system ahead of Jupiter and behind of Jupiter. And because of the mass of Jupiter and the mass of the Sun, those points actually accumulate asteroids. And so there are great groups of asteroids ahead of Jupiter in its orbit and behind Jupiter in its orbit. All of which is to say these balance points also are useful for us because they're places we can put spacecraft and have those spacecraft kind of sit there for a longish period of time without having to do very much. But they're not orbiting a planet. They're orbiting, the spacecraft is essentially hovering or orbiting around an empty point in space. But it's one of these extraordinary balance points. They're quite hard to conceptualize, but mathematically we can work out precisely where these points are, and we can then exploit them. So, for instance, the James Webb Space Telescope sits out at the Earth-Sun Lagrange point 2, or L2 point, and it actually performs what's called a halo orbit. So the spacecraft uses its thrusters to just nudge it around that empty point in space. And it's a great place to be because it's far enough away from the Earth that the telescope isn't impacted by the Earth's infrared radiation because the telescope is optimized to look at infrared light. So that's a little bit of a description of these Lagrange points. And they exist across the solar system. In any place where you have a pair of objects, you get Lagrange points.
Another thing that I really wanted to go into is life on other planets, whether that's in our solar system or even beyond. Now, immediately we think of life on another planet. Our thought is Mars. What is going to happen? We know that the moon is potentially, for us, habitable. Not saying that that's going to be the first place that we're going to look, but we're already looking at space exploration to Mars. Now, what's going to happen there? We're going to have a lot of different things that are coming about, and that includes everything from governance to supply chains. And you also mentioned that Mars may be a little bit of a siren for us. Do you want to tell us why? Because that's a loaded question.
Yeah, I mean, to put it in sort of simple, quick terms, Mars has long held our attention. Right. And some of this is because of misunderstandings a century ago about, what was going on Mars. We would look at it with our telescopes, and some people imagined they were seeing structures from some civilization on Mars and so on. And so we've long had in our heads that Mars is, not so different than the Earth, and it might be a good place to set up shop for humans. The truth is, Mars is extremely alien and a very, very different world than the Earth. But it is a sort of large planetary body, and it has had a history, a deep history over billions of years, where it's undoubtedly been much more hospitable, much more habitable, where it has had liquid water on the surface and so on. Today, it's an arid desert planet. In fact, a cold, arid desert planet
Yes.
with very, very little atmosphere, with sort of quite severe surface radiation, both ultraviolet radiation because of the lack of atmosphere and just cosmic radiation. The surface chemistry of Martian soil is quite caustic, contains these oxidizing compounds that are somewhat problematic. And the surface of Mars, if you're standing on the surface of Mars, you experience only a third of the gravitational acceleration that you do on the surface of the Earth. So Mars is Yet at the same time, I think we've all seen these pictures return from the surface of Mars, from rovers and other landers. And it looks kind of beautiful, right? It looks like the American Southwest. It looks like these wonderful sculpted hills and sand dunes and so on. So there's this strange thing that goes on in our brains where we sort of say, well, yeah, Mars seems like a good place to set up shop. If we wanted to really experiment with human settlement beyond the Earth, perhaps we should go to Mars. Some people think of Mars as a place where we build a sort of backup against existential risk. What if something really bad happens to the Earth? Preserve humanity and other species on Earth. We should have a backup. We should have, humans on a place like Mars. It's far enough away that whatever happens to the Earth, it'll carry on. But the truth is, and I call Mars the red siren, because
Yes.
on the one hand, it feels so appealing because there are similarities. We can kind of get our heads around what it would be like to be on the surface of Mars and so on. In every other respect, though, it's an appalling place. It's probably at least as challenging as the lunar surface to exist on Mars. We don't know what the long-term effects of things like reduced gravity are on the human body. We've never really done that experiment. The Apollo astronauts were on the moon so briefly that it didn't really tell us anything. The radiation environment and so on and so on and so on, and the isolation, the sheer distance from the Earth to Mars. So one of the things that I try to explore in the book is the range of options available to us for a place like Mars. What do we do? What should we do? Should we study it cautiously as scientists? Should we go all in and put, a million humans on the surface of Mars? Or should we leave it alone? Should we pay attention to the Earth first and not bother about Mars? I think there's actually another approach that's a bit of a mixture of some of the things that we've become really good at. So, for example, we could make Mars the most studied and most scrutinized planet in the solar system other than the Earth. We know how to do that. We know how to place satellites around a world and image it and sense the composition of the planet and monitor it, build communication networks, sort of digitize a world. Perhaps we should be doing that to Mars before we worry too much about sending people. We should make Mars the most sort of digitized, connected world other than the Earth. Do that first, gain understanding of the Martian environment that we don't have yet, and then start to think seriously about whether we put humans there. But perhaps humans on Mars is not really a long-term option. You could do better by creating artificial habitats where you can spin them up to generate artificial gravity. You can have complete control over the environmental conditions in a way that is very challenging on another planet, on a world like Mars. So, yeah, there are many questions about Mars, but I think there's a tendency to imagine that Mars is much easier than it really is.
So let's look at this on a grander scale. Do you want to paint us a big picture, whether that's 500 or 5,000 years from now? And when do you think that we're going to truly take the giant leap?
I actually think we're in the very beginnings of the giant leap right now. We're seeing this exponential growth in the launch of rockets from the surface of the Earth. We're seeing enormous growth in sort of the early days of what I would call a space economy. There's always been a space economy to some extent since the middle of the last century, but it's taking on a new form. There are now across the globe something like 10,000 space-related companies operating, which is kind of remarkable. We have roughly 30 locations on the surface of the Earth where launches can take place. I think we're beginning to see the first sort of nudge towards that giant leap. Where it goes, of course, is always going to be very hard to predict, but there are things that we know are true. So, for example, the sheer scale of our solar system, the sheer abundance of resources means that over the next century, over the next 500 to 5,000 years, the impetus, the motivation to do more and more off-world, to do more and more out in the solar system, that motivation is large. We know that there are quintillions of dollars worth of rare elements in asteroids around the solar system. That might be problematic for the Earth's economy because it would just disrupt the economy and, that much platinum or gold, suddenly platinum and gold isn't worth anything anymore. But the utility of those elements and things like rare earth metals, the utility of those for building technology really comes into its own in a space-based economy, an economy that is no longer just on the Earth, it's on multiple worlds, it's spread across the solar system, potentially in habitats that we construct, whether we build them out of asteroids or whether we build them entirely from scratch as artificial environments for ourselves. So I think one possible future that is also arguably a future driven by the kind of things that life does in general. Life expands. If life is presented with a new niche, it will move into it, almost regardless of whether or not we think that's a good idea. And I think we do have agency, but we also, as a species, when there are billions of us, things just happen. And it's not necessarily because of one person's decision or a group's decision. It's just there's an inevitability to some of the things that take place for us as a species. And I think space is one of those things. Hundreds of years, thousands of years into the future, what might that look like? We get back to this idea of dispersal, a dispersed humanity, dispersed civilization. There could be pockets that are of that civilization very different with different social structures. But the scale of it would also imply a difference in how industry operates, how societies operate, how we get material from one place to another in this future solar system and so on. So part of what I look at in the book are sort of the boundary conditions for this. We may not know what the details are, but we can ask what would be the ultimate extrapolation. I'll say this just because it's fun to kind of imagine this. If you actually look at the wealth of materials in asteroids and other objects scattered through the solar system, there's enough stuff to build thousands of biospheres and technospheres. There's enough energy from the sun to support trillions of humans, plus all of the biospheres that would be necessary to support those individuals. So the extrapolated version of this is something completely outside of our current experience, a scale of civilization, a scale of life, unlike anything that has happened on the Earth's surface for sure. Imagine a future with 50 trillion humans scattered across the billions of miles of the solar system. Sounds fantastical, sounds crazy. Why on earth would that happen? Well, the thing is, it could happen, and perhaps it will.
It sounds crazy.
It does.
Humanity with its current state.
But I would argue that the sheer scale of the solar system would mean that, let's say, those 50 trillion humans, then they wouldn't be squabbling over all the same stuff. They might be squabbling amongst themselves, but they would be so diluted and dispersed around the solar system that, at least somewhere there would probably be a functional society. It might not be everywhere, but there would be at least one place where things would function.
Out of curiosity, is there any thing that you want folks to take away from this conversation or even about space in general?
I guess the biggest thing I'd like people to take away from our conversation today and perhaps from the book is just that you may think that what's going on in space is kind of separated from your life, doesn't really play a role, doesn't matter so much. It's just, technology stuff. You can kind of ignore it. I would say that actually, unbeknownst to you, space exploration has had an enormous impact on all of our lives through what it's done for our understanding of the Earth, what it's done for our sort of day-to-day technology. And that's going to continue to be amplified into the future. So it is perhaps in your best interest to pay some attention to this, because understanding it may be helpful in making life decisions, may be helpful in appreciating where we're going as a species. So it's a surprisingly under-examined part of all of our lives, whether we like it or not.
Caleb, thank you so much for coming on the show. Maybe the greatest leap isn't into space, but into understanding our place in it. If life is the universe becoming aware of itself, then curiosity is its heartbeat. Until next time, keep asking beautiful questions, and as always, stay curious. And now a message from our sponsors. What is the Curiosity Box? It's the world's first subscription for thinkers created by Vsauce, the science network with over 23 million fans. Each season brings a new adventure in science, puzzles, and exploration, packed into a box designed to ignite your curiosity. The new box, a showcase of imagination and discovery. Try the 4D tape measure, part ruler, part pendulum, that measures both space and time. Play with Mr. Wiggle's Giggle Jiggle siphons, silly-looking straws that secretly reveal the physics of fluids, snap-on slap bracelets that double as rulers, cylinder measuring tools, and even tongue-in-cheek time-traveling credentials. Every collection is unique, filled with limited items you won't see again. Subscriptions start at $75 quarterly or $280 annually for even more savings. Available across the US, Canada, UK, Europe, and beyond. Check out thecuriositybox.com/breakingmath and get 25% off your first box with the code BreakMath25. The Curiosity Box, because discovery should never stop.